second part of the section involving formulas. And the last example we did in the first part, we took the formula P equals 2 times L plus 2 times W, and we rewrote it so that L was all by itself. So here's the formula we started with. And the only L we see is on the right-hand side of the equal sign. L is being multiplied by 2, and then there's something that is being added to the 2L. So the first thing we're going to do is we're going to subtract 2W from both sides of the equal sign. And on the right, now we have 2L plus 0. So that's just 2L. And on the left, we don't have like terms. So all we could do is write down that we're supposed to subtract 2W from the P. And then we said, okay, on the right, the L is being multiplied by 2. So if we divide that by 2, then we would have just one L. In other words, L would be by itself. So I have to take the entire left-hand side and also divide it by 2. So my left-hand side is now P minus 2W all over 2. Now, on the left, there's variables, constants, operations, but none of the variables are L, and the only L is on the right, and it's all by itself. And then we can interchange the left-hand side and the right-hand side of our equation. Because if one thing is equal to a second thing, then the second thing is equal to the first thing. So we have solved our equation for L, our formula that had started with 3 variables in it, started with P by itself, now L is by itself. Suppose we have that same formula, P equals 2 times L plus 2 times W. But this time we want to get W by itself. Well, if we're sort of pretending that P and L are numbers and W is the variable, some people might feel more comfortable if they rewrote the right-hand side. Because there's addition, we can rewrite that as 2 times W plus 2 times L. And so the variable term is first. So just like if we have 3 plus 5x, usually we rewrite that as 5x plus 3 with the variable term first. If that makes you feel better, you can go ahead and do that. The 2L is positive and the 2W is positive. And now the W, we can see that W is being multiplied by 2 and then something is being added to that. And we can undo that addition with a subtraction. Bring the equal sign straight down. On the left, we don't have like terms. All we can do is write down the subtraction. On the right, we've got 2w plus 0. So that's just 2 times w. And now to undo the multiplication that's happening to the w, we're going to need to divide by 2. So I need to take the entire left-hand side and divide it by 2. So we've got P minus 2 times L, all divided by 2, is equal to 1 times W, which is just W. And then we can rearrange, we can swap the left-hand side and the right-hand side of our equation. Here's another equation. Capital P equals capital R minus capital C. This time we want to get R by itself. What's happening to R? The formula is subtracting C from R. So to undo that, we need to add C to both sides. Draw the bar, bring the equal sign straight down. On the left, now we have P plus C, and on the right, we have R plus 0, so that's just R. And we can rewrite that then as R is P plus C. Now suppose we have that same formula, but this time we want to get C by itself. Before, we reminded ourselves that if we had an expression like 3 plus 5x, we usually prefer that to be written 5x plus 3. It just feels better. In our formula in problem 4, the C is coming after the R and there's a subtraction. Well, addition is commutative. We can change the order of the terms when we add, but not when we subtract. Subtraction is not commutative. That's the bad news. The good news is that every subtraction is an addition in disguise. Subtracting C is the same as adding the opposite of C. And so now that we have addition, we can change the order of the things that we are adding, the terms that we are adding. So we're trying to get C by itself. If we had the number C, we would find its opposite, then we would add R to that. So to undo things, we need to work in the reverse order. So we need to unadd the positive R by subtracting r from both sides. Draw the bar, equal sign straight down. The left-hand side is P minus R. The right-hand side is the opposite of C, plus 0, so it's just the opposite of C. But we need to get C completely by itself. Right now, the opposite of C is by itself. But remember, the opposite of anything is the same as -1 times that thing. So to get C by itself, we need to undo the multiplying of C by the -1. So we need to divide both sides by -1. On the right-hand side, -1 times C divided by -1 is +1 times C, which is just C. So now we have C all by itself on the right. We prefer our final answer to have the variable on the left. This time our answer on the right-hand side, now that we have switched the left and the right-hand side, we have a fraction. And in that fraction, the denominator is negative. Most of the time, we don't like having negatives in the denominator of a fraction. And we saw previously that one way to deal with that is to multiply the fraction by a name for the number 1, but written as -1 over itself. We have to be careful though, because the numerator has an addition in it, currently disguised as a subtraction. P minus R is the same thing as P plus the opposite of R. And so when we multiply through that fraction by -1 over itself, because there's addition inside the numerator of that fraction and multiplication outside the numerator of that fraction, addition inside, multiplication outside. If I want to simplify that, I'm going to have to distribute. In the denominator, -1 times -1 is +1. Oh, and then anything divided by 1 is itself. helps, you can put that -1 in parentheses there as well. So we have C all by itself. We could actually stop here if we wanted to. Some people prefer that when there's parentheses with addition being multiplied by something, that we use the commutative property of multiplication. To put that multiplier out in front. And then because we have multiplication outside and addition inside, we can distribute the -1 to both of the terms inside the parentheses. And now we have -1 times P plus +1 times R. In other words, we have the opposite of P plus R on the right-hand side. The right-hand side has two terms being added. They're in alphabetical order. P comes before R in the alphabet, which is usually how we write things. But sometimes when the first term is negative, we choose not to write them in that order. And so someone else might say, okay, I'm going to rewrite this now as R plus the opposite of P, which would be the same as R minus P. There are several different acceptable final answers. Unless I tell you that the other side of the equation, the formula, has to be in simplified form, you could stop as soon as you have C by itself and you don't have a negative in the denominator, because nobody likes a negative in the denominator. Or if you wanted to write the -1 first, that would be an acceptable answer. Or if you decide to distribute the -1, and we know that -1 times P is the opposite of P. You could stop there. The C equals the opposite of P plus R. And it would be okay with me if you wanted to do either or neither of these last two steps. And we could have an argument about which is better. To write C is the opposite of P plus R, because P comes before R in the alphabet. Or is it easier to think that C equals R minus P? For my purposes in these kind of problems, it doesn't really matter. Once you have C all by itself, that's the goal. As long as you don't have a negative in the denominator, and you don't have, say, a fraction inside of a fraction or a decimal inside of a fraction, the rest doesn't really matter. It kind of would depend on what you would want to do next as to which of these various ways of writing the answer you might prefer. Let's look at this same problem again in a slightly different way. We're starting with P equals R minus C. R minus C is the same as R plus the opposite of C. If you understand that the R is positive, you don't have to switch the order of the two terms on the right. You could choose to subtract R right now from both sides. And then you would have P minus R equals 0 plus the opposite of C. And the opposite of C is the same thing as -1 times C. So to undo that multiplication, we're going to divide both sides by -1. So we have P minus R all divided by -1 is equal to C. So in other words, C is P minus R all divided by -1. But we'd rather not have a negative number in the denominator. So like before, we could multiply by -1 over itself. And we have C is P minus R times -1 over +1. And so C is P minus R times -1. And then, as before, if I wanted to, I could put the -1 in front. And if I wanted to, I could distribute that -1. So this was essentially, we did the same steps as we did the first time, except for I didn't physically rewrite R plus the opposite of C with the term with C first. So the previous time I did this problem, once I wrote my subtraction as adding the opposite, then I switched the order of the terms because usually we like to see the variable term first, then the constant term. But this second person was able to realize that we need to subtract the R because the R is being added to the opposite of C, and this R is a positive 1R, so we need to add a negative 1R, or we need to subtract 1R from both sides. A third person might start with this same formula and say to themselves, self, I'm being asked to get the variable C by itself. And the way the formula looks right now, C is being subtracted on the right-hand side. And I know that I can add anything I want to both sides of my equation. So if I want to, I could add C to both sides of my equation. And my left-hand side would be then P plus C. And my right-hand side is going to be R minus 0, which is just R. But I have to remember I'm trying to get C by itself. Oh, well, P plus C on the left is the same thing as C plus P. And if I'm trying to get C by itself, all I need to do is subtract P from both sides. To undo that addition, and now I've got C plus 0, so that's just C, equals R minus P. C is by itself. The right-hand side is just two variables being subtracted. We're done. In problem 5, we've got D equals R times T for our formula. If it helps, we can make the multiplication explicit instead of implicit. We want to get little t by itself. Little t is on the right. It's being multiplied by R. So to undo that multiplication, I need to divide both sides by R. Then I have D over R is equal to T. So T is D over R. It helps to put a tail on your lowercase t's so they don't start looking like addition signs. Question 6 is starting with the same formula, D equals R times T, But this time we want to get R by itself. Right now, R is being multiplied by T, so we need to divide both sides by T. The left-hand side is now D divided by T, and the right-hand side is R, little r, times 1, which is just little r. And then we can interchange the left-hand side and the right-hand side of our equation so that r is on the left. R is on the left all by itself. On the right, there aren't any r's, so we're done. Here's our simple interest formula. I equals PRT, in other words, P times R times T. We want to get little t by itself. On the right-hand side, the only operation is multiplication. And multiplication is associative. So P times R times T can be thought of as P times R, that result times T. So what's happening to the T? The T is being multiplied by both the P and the R multiplied together. So to undo that, to undo parentheses times T, we need to divide both sides by what's in the parentheses, which is P times R. So now we have I over P times R. We can still have those parentheses if we want. But when we write a fraction with a horizontal fraction bar, there's an implied set of parentheses around both the numerator and the denominator anyway, even if we don't write them. And on the right-hand side, we've got 1 times T, which is just T, because whatever P times R is, P times R divided by itself is 1. And so T is equal to capital I divided by the quantity P times R, and we can choose whether or not we want to write the multiplication sign. We could take that same formula, I equals P times R times T, and we can rewrite this formula so that P is by itself. This time, on the right-hand side, I want to think of the r times t, I want to associate those two together. And I can do that because the right-hand side has only multiplication, and because multiplication is associative. So now, in order to get p by itself, I need to undo the multiplication of the stuff that's inside the parentheses, which is r times t. So I have I over r times t is equal to p. So in other words, p is equal to I over r times t. I don't need the parentheses and I don't need the multiplication sign if I don't want to write them. I may write them. I don't need to write them. Okay, well, what if we have the same equation, the same formula that we're starting with, but this time we want to get r by itself? Well, again, I is p times r times t. Multiplication is associative and it's commutative. We can change the order of the three things that we are multiplying together, and we can write p times t times r, and we can think of p times t as if it's a single number that then is being multiplied by r by using the associative property. And so to get r by itself, we have to undo multiplying the r by the parentheses of p times t. So we're going to divide both sides by the quantity p times t. So we have I over the quantity p times t is equal to r. And so r is equal to I over p t. And I don't need to write the multiplication sign or the parentheses if I don't want to. I may if I do want to. Here's a problem where the formula involves a fraction. The right-hand side can be thought of 360 divided by n. We want to get n by itself. Right now, n is in the denominator. But we have an equation with fractions in it. We can clear our fractions by undoing the division by doing a multiplication. And we want to multiply both sides of the equation by the denominator. Because that will clear our fraction for us. And now we have n times e is equal to 360. Because on the right, the n's divide out and we have 1 times 360 is 360. So now the n is no longer in the denominator, it's in the numerator. And it's being multiplied by e, capital E, and we want to get n by itself. So we need to undo the multiplication with a division. And we're going to divide both sides by e. And so we have n times 1, which is n, is equal to 360 divided by e. In other words, 360 over e. Sometimes your formula has a bunch of stuff multiplied together, and one of those things is a fraction. We can use sort of the same strategy we just used. We can think to ourselves that h is being multiplied by b and then being multiplied by 1/2. And we can think of the b and the h as being divided by 1. So we can think of the right-hand side as b times h, then divided by 2. And we can clear our fraction by multiplying both sides by 2. On the right, the 2's will divide out. So on the left, we have 2 times a, which we can just write 2a. And on the right, now we have b times h. And right now we're trying to get h by itself. So we're going to divide both sides by little b. And when we do that, the left-hand side is now 2 times capital A over little b, and the right-hand side is 1 times h, which is just h. And so we get h is 2 times A over little b. Problem 12 starts with the same formula, but this time we want to get little b by itself. Capital A is 1/2 times b, which is b over 1, times h, which is h over 1. So 1/2 times b times h is the same thing as b times h over 2. Again, we'll multiply both sides by 2. On the right, the 2's will divide out. So we have 2 times a equals b times h. But this time we're trying to get little b by itself. B is being multiplied by h, so we need to divide both sides by h. So 2 times capital A divided by lowercase h is equal to lowercase b. So b is 2 times A over h. This formula is a little different than some of the others we have seen. It has two variables in it, x and y, but neither of them is right now all by itself. But we want to get the y all by itself. Nine times x plus 4 times y is 108. Usually we think of x as the variable, but in this problem, they want us to pretend y is the variable, but x is a number. Usually, we like to have the variable term first. So just like before, if we had 3 plus 4y, that's the same as 4y plus 3. And that feels better to us because we made this agreement before that we like to have the variable term first and then the constant term. So I could write the left-hand side as 4y plus 9x equals 108. So the y is being multiplied by 4, and then this stuff, 9x, is being added to that. So we need to undo that addition with a subtraction. Bring the equal sign straight down. The left-hand side is 4 times y. The right-hand side is 108 minus 9x. Oh, but now the right-hand side has the variable in the second term instead of the first term. Maybe we care about that, or maybe we don't. If we do, we need to think of subtracting 9x as adding negative 9x. And then we can change the order of those two terms. And we're trying to get y by itself. Y is being multiplied by 4. So now we want to divide by 4. And we have to be careful to make sure we divide the entire right-hand side by 4. So now we have 1 times y, which is just y, equals the quantity negative 9x plus 108, all divided by 4. And you need to make sure that our fraction bar sticks out in front of the negative sign for the negative 9x. This problem 14 is very similar to problem 13. The only difference in the original formula is that right now the 4y is being subtracted instead of being added. But every subtraction is a disguised addition. And in this problem, we're being asked to think of the y as the variable and to sort of pretend that the x is a constant. And so 9 times x, we're pretending is a constant. We have to unadd before we unmultiply, so we need to subtract 9x from both sides. Bring the equal sign straight down. Now we have negative 4y plus 0, so that's negative 4y, is 108 minus 9x. Even though we're pretending x is a constant, it really is a variable. And we prefer to have variable terms first. So subtracting positive 9x is the same thing as adding negative 9x. And so on the right-hand side, I can rewrite that as negative 9x plus 108. And now I can think about the left-hand side. It's negative 4 times y. So if I divide by negative 4, that would be positive 1 times y. And so that's going to be just a positive y. So now I have y all by itself. I have to be careful that my fraction bar on the left extends under the negative 9 in the 9x. And yes, I have y all by itself, but my denominator is negative. And we don't like to leave fractions with a denominator that's negative. So I could multiply this fraction by negative 1 over itself. But I'm going to have to be careful in the numerator to put parentheses in. And I probably want to think of the numerator as negative 1 times negative 9x plus 108, rather than parentheses negative 9x plus 108, then times the negative 1. But the denominator is now positive 1, so that's good. Positive 4, excuse me. It was negative 4 times negative 1, that's positive 4. And I could leave my answer like that, or maybe I want to distribute the negative 1 in the numerator. So now I have y equals positive 9x plus negative 108, all divided by positive 4. Sometimes there are formulas that have fractions and parentheses in them, like the formula for converting a Fahrenheit temperature into a Celsius temperature. there's an implied multiplication between the 5/9 and the parentheses. And inside the parentheses, F minus 32 is the same thing as F plus negative 32. And right now, this F is trapped inside the parentheses, but the F and the negative 32 are not like terms, so I can't actually add them. But I can get F out of the parentheses if I distribute my 5/9. 5/9 times F, but F is F over 1, plus 5/9 times negative 32 over 1. So now I can rewrite this equation as C equals 5F over 9 plus negative 160 over 9. And now I have lots of options. One option would be to write the C as C over 1 and multiply it by 9 over 9 to get a common denominator for every term in the entire equation. So I have 9 times C over 9 equals 5F over 9 plus negative 160 over 9. And I can clear my fractions if I multiply the left-hand side by 9, and I multiply the right-hand side by 9. The left-hand side is now the same as 9 times 9C over 9. And I'm thinking of those two 9s dividing out. And on the right, now I have addition inside the parentheses again, and a multiplication outside the parentheses. So I need to distribute that 9. So I'm going to have 9 times 5F over 9 plus that 9 times negative 160 over 9. But now in each of my fractions, my 9s divide out. So I have 9 times C equals 5 times F plus negative 160. And I've cleared my fractions, and I want to get my F by itself. F is being multiplied by 5, and then negative 160 is being added. If I add 160 to both sides, draw the bar, equal sign straight down, the left-hand side is now 9 times C plus 160, and the right-hand side is 5 times F plus 0. And so I can get my F by itself if I take both sides of my equation and I divide by 5. So my left-hand side is 9C plus 160 over 5. And my right-hand side is 1 times F, which is just F. And then I can interchange my left and my right-hand sides so that the F is all by itself on the left instead of on the right. There's a slightly different way we can approach the same problem. Again, C is 5/9 times parentheses F plus negative 32. I can think of that entire parentheses on the right as being a single thing. And I know that anything divided by 1 is itself. So I can turn the parentheses into a fraction by saying parentheses divided by 1. And then I can think of the right-hand side as multiplying two fractions together. And the process for multiplying fractions is that we multiply the numerators and we multiply the denominators, but 9 times 1 is just 9. So instead of thinking of the fraction 5/9 times parentheses, I am now thinking 5 times parentheses, then divided by 9. I can undo that division if I multiply both sides by 9. So 9 times some stuff, then divided by 9, those 9s divide out. And now I have 9 times C, which I can just write as 9C, is 5 times parentheses, F plus the negative 32. I could distribute my 5 now, or I could undo that multiplication of 5 times parentheses. I could divide both sides by positive 5. So now I have 9 times C divided by 5 is 1 times F plus negative 32. But 1 times anything is itself. So the right-hand side is just F plus negative 32. And there's only one operation now on the right-hand side, so I don't need parentheses. And I'm trying to get F by itself. And I can do that now if I add 32 to both sides. Draw the bar, equal sign straight down. The left-hand side is now 9C over 5 plus 32. And the right-hand side is F plus 0, that's just F. So I have F equals 9C over 5, then plus 32. And my answer looks a little different than the answer I got the first time I did the problem. But the first time I did the problem, on the right-hand side, I have a single fraction, whereas this time I have two different terms being added. And notice what happens if I were to get a common denominator. I would need to multiply the 32 by 5 over 5. And that would be 160 over 5. And if I added those two fractions together, I would end up with this. So both of these people are correct. Sometimes the fact that there are similar but slightly different ways of looking at the same problem is confusing when you're trying to get help from some source, whatever that source is, a friend, a tutor, a book, a website. Because the way you are thinking about the numbers and the operations is maybe slightly different than the way your tutor is thinking about them. And in these kind of problems where we are rewriting formulas to get a different variable by itself, those kinds of different ways about thinking about the problems can come up in the middle of a problem, and it makes it a little bit hard sometimes when you're chatting with someone else. If one person is trying the problem one way and another person is trying the same problem a slightly different way. It might be that you both are correct, but you're just thinking about the problem slightly differently. Or it might be that one of you is making a mistake. Take care. Thanks for listening. I hope this process of solving a formula for a different variable is a little less intimidating than it was at the beginning of this video. And we'll see you in the next video. Take care.